Good morning, everybody, and welcome again to the CEIA Maths Tutorials Online. This week we have the statistics tutorial with Frank O'Keefe.
Thanks, Eamon. Okay, so let's dive right in. So today, these are the topics I'll be covering, starting with frequency distributions, then go on to measures of center, which is averages, measures of spread, especially standard deviations, divert a little bit to talk about bivariate data and correlations, and then on to the meat of the course, which is normal distributions and the standard normal. We talk about inferential statistics then and hypothesis testing, look at significance, a test of significance, which is the p-values, and hopefully I'll have a good amount of time to spend on the exam questions, doing some examples to illustrate some of those previous topics. Right, so let's dive right in with frequency distributions. So we start with a data set, a set of observations of some variable. It needn't necessarily be a set of numbers, but most of the cases we look at are a set of numbers. And if you do have a set of numbers, and I've given an example set here, it's helpful to order them. And once you order them, you can see that you get repeated values of some items. And that leads us to a frequency table where we list the number of times each item occurs. So each item xi, you see 1, 2, 3 don't occur at all, 4 occurs once, 5 occurs twice, and so on. The most common one there would be 8, which occurs 4 times. So the frequency table is a more concise representation of the data set. And it lends itself to graphing easily using a histogram, where you just use vertical bars representing the frequency of each data value. Right. Now in the previous example, we used each unique data value for an entry in the frequency table and a bar on the histogram. But you can have different size intervals where you group the x values, in this case, intervals of 3, so 1 to 3, 4 to 6, and so on. You get a smaller number of bars with more items in each bar, or a bigger frequency within each interval, if you like. Now, what happens if you've got a very large data set, which is typical in statistics? Well, you can draw it as, again, as a frequency table or a histogram with a large number of closely spaced bars in the histogram. At some stage, though, that becomes impractical. And instead of drawing the bars, you can just draw the tops of those bars and connect them with a curve. And when you do that and just leave the curve, that's called a frequency distribution curve. But it's essentially the same data as was in the frequency table. Now, just as an aside, I'll mention that there are other representations, stem and leaf and pie charts and so on, which we're not going to talk about much here. They're not asked very often, but they could be asked, and they're more junior sort of levels. So you still need to be aware of them, and things like quartiles and percentiles and so on. You still need to be aware of them, so do read through them, but we're not going to talk very much about them here. So back to the frequency distributions. And an important class of frequency distributions are normalized ones. And normalized ones are where you ensure that the total area under a frequency curve is 1. And you do that by taking your original frequency curve, working out the area under it, A, which is just an integral over all x. Find that A and then divide every point in your frequency curve by that number A. And you get a normalized frequency distribution. Right, and the reason you do that is that a normalized frequency distribution is a probability distribution function. The reason being that, if you go back to the curve there, that if all the probabilities of any event must add up to 1. So if you normalize the frequency distribution so that all possible values add up to 1, then it's equivalent to a probability distribution. And the way you need to interpret the probability distribution function is if you consider any values a and b of your variable x, then the probability of a data sample lying between a and b is equal to the area under the curve, the frequency distribution, the probability distribution between a and b. Now, the main frequency distribution or probability distribution function that we'll use in this course is the normal distribution. It's the most commonly used one in statistics. You might hear it called a Gaussian distribution or a bell-shaped curve or a bell curve. And it takes this general shape. So as you can see, it's approximately bell-shaped, and it occurs in many random processes. I've listed a few here, but it's almost universal. And it's the one that the Leaving Certificate course concentrates on. Now there's a special case of that normal distribution called the standard normal. And this is where you have a standardized size and width of that normal distribution, but it's centered around 0. So more commonly, the ordinary normal distributions will generally be centered around some average, which is quite often a positive value. Not universally, but quite often a positive value. For example, if this is a graph of people, the frequency of people's heights, then obviously that's going to be a positive number. For all values are going to be positive, and it'll be centered around some average. Whereas the standard normal is centered around 0. So you can see it's shifted to the left, and it's also generally not the same width, even though it may look like I've drawn it the same width here. We're going to come back to this later because it is very important. Now let's talk about measures of center or averages, and we go back to our sample data set as an example. And the measures of center you need to know about, they include the mode, which is the most common value. And if you run through our data set there, it's 8 is the most common value. It's the one that will be the peak of your frequency distribution curve. The median is the one that's halfway along the ordered data set, so that half the numbers are below and half the numbers are above. It's 8 again in our case here. And then there's the mean, which is what is commonly meant by average. And the mean is the sum of all the values divided by the number of values. So that's a simple representation of it, but it's usually easier to calculate it using the frequency table, like so. So you multiply each data value by the frequency, the number of times it occurs, and divide that by the sum of those frequencies, which is the same as the total number of data points. Now in terms of usage, while mode doesn't always exist and it isn't used very much, but it is occasionally used, the median is used more, and it is often used to eliminate skews or outlying values. An example often given is if you have 10 people in a room and you want to know their average salary. You know, if there's a billionaire in the room, it distorts that average if you're looking at the mean. But if you have the median, it gives you a truer representation of what a typical person would have. And of course, mean then is the most common measure, and that's the default meaning when we talk about an average. Interestingly, if you have a normal distribution, these three values are all the same. Now, just as an illustration of the calculation of the mean, with our data set, you take the frequency table, and you've got one entry of 4, 2 of the 5, 2 of the 6, 3 of the 7, 4 of the 8, 3 of the 9, and so on. Multiply them all out and add them up, and divide it by the total number of elements in the data set. You get 160 over 20, which in this case is 8 again. Now, measures of variability, measures of spread. Well, the easiest one is the range, which is the difference between the lowest value 4 here and the highest value 12. So the range here is 8. You can have some outliers in this data set, which means that might not be a reliable measurement of the spread. To eliminate that, people sometimes use the interquartile range. So you look at the lower quartile, which would be around here, say about 6.5, with a quarter of the values below it, and the upper quartile, which would be up at 10, or actually maybe 9.5, in fact, with a quarter of the values above that, and subtract the two, and you get the interquartile range. I'm just looking here now and think that probably should be 9.5 rather than 10. So it should be 9.5 minus 6.5, which is 3 rather than 3.5. However, the most commonly used measure of a spread is the standard deviation, and that's the one we're going to use for the rest of this tutorial. And what that is, it's, well, in short, it's the root mean square deviation from the mean. What that means is if you take the distance of every data point from the mean, you'd like to average all of those distances somehow. But if you were just to take the average of them, some of them will be positive and some will be negative, and they'd cancel out. So it's more common to square them, square those differences to ensure you get a positive value, and then take the average of those squares and then take the square root of that. So in the case of our data set, you take each data point and subtract the mean from it. So for 4, it's 4 minus 8. Square that and multiply the number by the number of times that the 4 occurs, and so on. For example, the 9 here occurs 3 times, so it's 9 minus 8 squared times 3, and so on. Add them all up and divide them by the number of points, and finally take the square root. In this case, it gives us about 2.2. So if we look at what the standard deviation actually represents, we can look at two frequency distributions here. They've both got a total area under the curve of 1, so they're probability distributions. But one of them is spread out widely, so that has a large standard deviation, and the one of them has a much tighter grouping of data points, so that's got a small standard deviation. Right, let's talk a little bit about bivariate data. That's where you have a relationship between two variables, which we represent as X and Y. It's common in statistics to try to look at a relationship between two variables and try to see if there's any causality involved, for example, or at least any correlation. Some examples would be you might look at how a person's life expectancy is dependent on the number of years of education they have. Or in astronomy, there is a famous relationship between the color of a star and its size. It's called the Hertzsprung-Russell diagram. So We represent these graphically using XY scatter plots, where one of the variables is plotted as X and the other is Y. And each pair of corresponding values appears as a point on the XY, on the XY plane, on the scatter plot. Now, one of the reasons you do those scatter plots is to look for correlations, to see if there is any dependency of one variable on the other. And for example, you could have a positive correlation where as one of the variables increases, the other one tends to increase as well. So you get an upward slope on average. And there are many examples of what kind of relationships would have positive correlations. Like, the cost of many items versus their size would be a positive correlation. Large countries tend to have, or countries with large areas tend to have large populations. It's not a perfect not a perfect relationship, but it is generally true. So you would expect this kind of rising trend for positively correlated variables like that. You could have negative correlations as well. I've chosen an example there. A famous one is that the more cigarettes smoked per day, the shorter the life expectancy you would expect. And it may not be a perfect straight line, and generally it isn't. But you do see a trend, and that trend is called the correlation. Sometimes, though, there's no correlation, and you see no relationship between one variable and the other. I've chosen a kind of a silly example there, that the size of an animal compared to the size of its name in terms of number of letters, there's no real relationship there. Like a caterpillar isn't bigger than a bear simply because the name is bigger. There's no correlation at all in that case. We can try to quantify the correlation using something like a correlation coefficient. There's a rather complex formula for this. Is one variety of correlation coefficient. It would be extremely tedious to try and calculate this by hand. You can do it. Some calculators will do it for you. If you enter the data set, enter all the X's and Y's together, all the XY pairs, let's say. Even that's quite tedious to do. But you should know at least how to interpret the correlation coefficient. It goes from -1 to 1. A strong positive correlation is where the R is close to +1. And a strong negative is where it's close to -1. If it's positive but not close to 1, then that would indicate a weak positive correlation. And if it's negative but not close to -1, then that's a weak negative correlation. If it's around 0, then you consider the data to be uncorrelated. But you can see it's an imperfect science, deciding what is strong or what is weak. And just some illustrations of those correlations there. Here's a strong positive correlation where it's almost a straight line relationship between X and Y. For a weak relationship, a weak correlation, you do see a general trend, but it doesn't lie close to a line. And similarly with negative correlations, you've got the strong one, which is nearly a straight line, and the weak one, which is more of a general trend. Now, one thing you'd like to do is to quantify the relationship between X and Y variables. That's called regression, and in this course you only need to consider linear regression, which is a linear fit to the data. It's a best line estimate of that linear relationship. So you try to fit a straight line through the data. And once you do that, you would be able to extract the slope and intercept of that straight line. And you can formulate a relationship in the form y equals mx plus c relating to data. And that process, as I said, is called linear regression. A lot of calculators will be able to do that. If you enter the x and y points, they'll return the m and the c for you. But you can do an approximation just using a graph. Do your best fit approximation by eye. Try to follow the general trend of the points. If it's available, you can go through this average point, which is the average x, average y. It may not actually be a point on the graph, but you can calculate it and put it there, and go through or near that point and try to keep half the points above and half the points below and half the points to the left and half the points to the right. And once you've done that, you can use your usual method of calculating the slope and measuring the intercept. So you get m and c. Right. So let's go back to the normal distribution now, because that is probably the most important thing in the course. And look at it in more detail. Every normal distribution is defined by two values. Its mean, generally called mu, but sometimes it's called x bar. And the standard deviation, which is represented by sigma. And it is an important empirical rule, which you do need to remember. In particular, you need to remember the middle one here, but there are three aspects of the empirical rule. And that's saying that if you take a normal curve, then if you go to one standard deviation, which is this length here, sigma, on either side of mu, so from mu minus sigma, which is here, to mu plus sigma, which is here, then the area under the curve here is 0.68. And that says that for a normally distributed variable, 68% of all values lie between the mean minus one standard deviation and the mean plus one standard deviation. More importantly, 95% of the values lie within two standard deviations of the mean. So between mu minus 2 sigma and mu plus 2 sigma. Now, actually, it's not quite 2. It's 1.96, and you should remember that it is 1.96 for accuracy. Sometimes people just approximate it with 2. And if you actually go 3 sigma out, 3 standard deviations, then almost all of the points lie underneath the curve between mu minus 3 sigma and mu plus 3 sigma. It's 99.7% of all values. Okay, so this is, particularly this middle one, are essential to remember. And I'd say a good 30 or 40% of exam questions, you'll be applying this. Now, if we look at the standard normal again, we compare, this is any normal distribution, and this is the standard normal down here. And I've drawn them this time so that they're on top of each other, but in fact, we've shifted the axis here. So the general normal distribution is centered on mu, the average value, and the standard deviation is sigma. Whereas the standard normal, the mu is 0, and the standard deviation is 1. So what would be minus 1 on the standard normal is equivalent to mu minus sigma on the general normal distribution. And similarly, plus 2 on the standard normal is equivalent to mu plus 2 sigma on the general normal. So the generally the variable for the standard normal is called Z as opposed to X for the general normal. And there is a one-to-one correspondence between points on the normal distribution and the equivalent point on the standard normal. And what the relationship is, the standard normal tells you how many standard deviations any point on the normal distribution is away from the mean. The reason to use the standard normal is because there's only one set of values for it. It can be tabulated, and it is tabulated in your log tables. So I'll just quickly flick to the log tables there. And this is, the format may have changed a little bit in the newer editions of the tables, but it'll be the same data. What is being plotted is the area under the curve, under the standard normal curve, up to some value Z1. Right, and you look up Z1. You may need to go into, for example, if you want to find 0.73, you go to the 0.7 and over to 0.03, and you find this value here, and that's 0.7673. Right, so it's very important that you familiarize yourself with the use of this table, because roughly, I would say more than half of all exam questions require you to use this table. Right, so going on here, this is a little bit more about the standard normal. We'll go through some examples. Now, to use the standard normal, you need to change from your original variable x, which is generally the value that you're studying, the real life value you're studying, and converted it as dimensionless quantity z. And the way you do it is you subtract the average, the mean of the x values from x, and divide it by the standard deviation, sigma. And what you get then is value quantity z, which is the number of standard deviations that your data sample x is from the mean value mu. And as I said before, this standard normal is plotted in your log table, although the normal itself isn't plotted, but the definite integral, let's say the area under the curve up to a certain point, is what is plotted, or is what is tabulated in the tables. The normal function itself is plotted, but the tabulated values are the integral. Now, because this is so important, I'm going to run through a few examples on how to use it. Again, to reiterate, the tabulated value is actually the area A corresponding to a value Z1, which represents the probability that that your variable Z is less than or equal to Z1. Now, so if we want to find the probability that a number is less than Z1, we can just read that straight from the table. Unfortunately, they only plot half of the values, so they only do it for, that's a typo there. This is actually, that should be 0. It's only tabulated for Z1 greater than or equal to 0. Sometimes the Z1 will be less than 0. Excuse me, I need to check to correct this, but that should read 0 here. And we want to know the probability. Sometimes the probability that Z is less than 0. Other times you want to know the probability that Z is greater than some value Z1. or we want to know the probability that Z lies between two values, Z1 and Z2. So we can't directly read any of these from the table. So what you need to do is, well, there's some tricks there. You use the fact that the graph is symmetrical about the y-axis. That lets you work with values of Z that are less than 0. You can use the fact that the area under the whole curve is 1. We'll show how that works in a minute. And for these more general cases where you're looking for values, but the integral between two values, Z1 and Z2, you try using sums and differences of areas to work out your desired probability. So let's work through some examples. Suppose you want to find the probability that Z is greater than -2. Right. What you're looking for then is the area starting from -2 on this curve all the way up to, well, plus infinity. So this shaded area here is what you're looking for. But this isn't tabulated. So you try to convert this to something that is tabulated. And we use the symmetry of the curve and redraw it this way and say, well, this area is the same as this area. So this area here, which is tabulated, is the same as the desired area here. So that is saying that the probability that Z is greater than or equal to -2 is the same as the probability that Z is less than or equal to 2. That is a tabulated value, which we can now look up. So we try to find Z is equal to 2, and we need to go to next set. And for Z equals 2, the value is 0.9772. Sorry there, I've gone here, yes. Okay, so that's our result, that the probability of Z being greater than or equal to -2 is 0.9772. Right, we've exploited a symmetry. This is what we're looking for. This is what is tabulated. So we're using symmetry to say that those two are equal. And the interpretation here is that 97.7% of all values are more than, are greater than a value that's 2 standard deviations below the mean. Right, look for a second example here. We're looking for the probability that Z is greater than or equal to 2, which is this area over here. Again, that's not tabulated. This area, which I've called A2, which is the probability that Z is greater than or equal to 2, isn't tabulated. But this area here, A1, is tabulated, and that represents the probability that Z is less than or equal to 2. Actually, I've written -2 there. That should be 2. So what we do is use the fact that this area A1 plus this area A2 add up to 1. So that the desired area A2 is 1 minus A1, which means that the probability that Z is greater than or equal to 2 is equal to 1 minus the probability that Z is less than or equal to 2. And again, we had that value from the table. It was 0.9772 from the table. So the probability of Z greater than or equal to 2 is just 1 minus this tabulated value, which is 0.0228, which is saying that 2.28% of data samples are more than 2 standard deviations above the mean. Now, this is worth remembering, this particular result, and generalizing it for any value of Z1. The probability that Z is greater than or equal to Z1 is 1 minus the probability that Z is less than or equal to Z1, knowing that this last term here is what's tabulated. Again, apologies. I've up here, I've written -2. That should just be 2 there. And that should be 2 there. But the rest of this is correct. Right. Another example. Supposing we want to find the probability that Z lies between two numbers. In this case, we've got 1.54 and 2.56. How do we work that out? Well, we can consider it as being the difference between two areas, which I've called, well, this area A1 is obvious. It's the probability that Z is less than or equal to 1.54. And this bigger area A3, which is also tabulated, is the probability that Z is less than or equal to 2.56. And visually, you can see that you get the desired area A2 here by subtracting area A1 from area A3, with A1 and A3 both being tabulated. So A1 is the probability that Z is less than or equal to 1.54. Find 1.54 here, it's 1.5. I go over to the 0.04, and we get 0.9382 here. A3 is the probability that Z is less than or equal to 2.56. Again, return to our table. We're looking for 2.56 in the table. Here's 2.5. Go over to 0.06 and we find 0.9948. Here. Right, so then our desired area here, A2 is A3 minus A1. Again, sorry, that's A2, not A3. It's A2 is A3 minus A1, 0.9948 minus 0.9382. And we get 0.0566, which is 5.6% of values lying between 1.54 and 2.56. Let's do one more example. I'm dwelling on this quite a long time because this is vitally important for exam questions. So it's really important that you do get practice at doing this. Find some examples, some questions in your textbooks and just run through them yourselves. So you get very familiar with this kind of manipulation of the standard normal. So let's look at the probability that Z lies between -2 and +1. Right, so that's this area here that I've drawn between -2 and +1, the area under the curve there. How do we find that? Well, we can easily find this area A1 here, which is the probability that Z is less than or equal to 1. To get this area A, we would need to subtract off this little bit here, which is area A2 that I've drawn here, which is the probability that Z is greater than or equal to -2. Now this area A1, that value is tabulated. We can find that probability Z is less than or equal to 1. Quickly going back to the table, to the previous page, and it's 0.8413. 0.8413. A2 isn't tabulated, so we're going to need to use symmetry to find that because it's on the wrong side of the curve. Remember, only values of Z greater than 0 are tabulated. So we use symmetry. We look at this picture instead, and we see that this area A2 is the same as that area A2. That area A2 is 1 minus A3, where A3 is the probability that Z is less than or equal to 2. So we get A2 is 1 minus A3, 1 minus the probability that Z is less than or equal to 2. That's the same tabulated value we found before of 0.9772. and that is 0.0228 for A2. And we need to subtract A2 from A1. So we subtract this value from this value, and I get 0.8185. So that tells us that 81% or 82% or thereabouts of values lie between -2 and +1 standard deviations from the mean. Okay, so I'll pause there just to see if there have been any questions to date.
No
Eamon,
open
no?
questions at the moment. There was a few questions that I hope were answered in the Q&A, but all good so far. Thanks, Frank.
Good. Okay. Right. Let's move on. And we look at applications of the standard normal, and so in the course, most of the exam questions will be either on direct application of the standard normal or on inferential statistics using the normal distribution. Right, and the idea of inferential statistics is that you look at a sample, a subset of data, and you try to infer characteristics about the main population from that subset, from that sample of the data. A sample could be a survey, or it could be some other means of sampling. And the problem is that this sample is generally, it's not a perfect representation of the whole population because it doesn't contain the whole population. And there's going to be some randomness associated with your selecting the sample. And then, well, you can ask the questions, what can we infer about the population from the sample? And how much confidence do we have in what we've inferred? And can we put margins of error on what we have inferred? Now, there are two classes of problems that we look at. And one is where we try to infer population proportions from sample proportions. That's where we're looking at what proportion of the population have some characteristic. I'll give an example here. We're saying, 40% of a sample of 100 people have blue eyes. What proportion of the whole population has blue eyes? Your first guess would be 40%, but that would assume that your sample was a perfect representation, which it generally isn't. So you need to estimate the error or the margin of error in this estimate. The second class of problems is to infer population means from sample means. What that means is that if you take a sample and measure some characteristic, some average characteristic of that sample, how good a representation is that of the average of that same characteristic for the whole population? I'll give you an example here where you have a sample of loaves of bread and you measure their average weight, and you try to infer what the average weight of the call it a population. Population doesn't mean people in this context, it just means the full data set. What is the average weight of the loaves of bread, of all of the loaves of bread? And how accurate is this 800-gram estimate for that? So let's talk a little bit more about that. First of all, the proportions. So you can talk about a population having a proportion, which we label P, that have some characteristic. Now, if you take a sample of that population, you're probably going to get something similar, a similar proportion in the sample that have that, that same characteristic. But while it's similar, it won't be exactly the same generally because of random sampling. And the error you get when you're sampling is called the margin of error, which we call E. So E is the difference between the sample's estimate of the proportion and the actual proportion P. And it's the absolute value of that because it can be positive or negative. You can get an error in either direction. So having taken a sample, well, let's state it this way first. If you take a sample, it can be different from the real proportion by an amount E. So your sample proportion that you're estimating from the sample can lie between P minus E and P plus E, where P is the real proportion of the whole population. Now, how big this E is depends on what confidence level you want to have, and we'll talk more about that later. It also depends on the sample size. Now, in a lot of practical problems, though, this shows you what error you get, what error will arise from the sampling process, and shows that your sample's P hat lies in a certain range around the real P. In practice, you want to work the other way around. In practice, you're going to measure your sample P hat, and you want to know what the real P is for the whole population. So you normally do it the other way around and say, again, the same margin of error, but now the real value P of the whole population lies in a range around the P hat that you've got from the sample. And this is the version of the margin of error formula that you'll actually use in most cases. Now, how do we calculate that margin of error? Well, there is a shortcut way of doing it, and that's use the formula. The margin of error is 1 over root n. And that, where n here is the number of data points in the sample. So it's the sample, the size of the sample. And then you can be 95% sure that the population proportion P lies within this much on either side of the P hat, which is what you've measured from the sample, the proportion that you've measured from the sample. So for this quick and dirty calculation, using E is 1 over root n, this becomes the confidence interval. It's called an interval because this is the range of values in which P is 95% likely to lie. Now, I said this is quick and dirty. It is used, but it generally is only accurate if your value P or the P hat are close to 0.5. And sometimes it's all you have to work with because you may only know the sample size. And then this will give you, this only works with 95% confidence interval as well. There's a more accurate way of calculating it, and that is using the standard deviation of the sample proportion, which is what was labeled here as sigma P hat. Now this formula is in the log tables, but in some editions of the log tables is written as the square root of PQ over N. So that's just a warning there, where Q is 1 minus P. But this is the version of this formula that you should remember. right? The square root of p times 1 minus p over n. So if you know p, then you can work out this standard deviation in p. Sometimes you actually don't know p because you've only got p hat. Since generally p hat is close to p, you would then use p hat in this formula instead of p. And that's valid for working out this standard deviation. And once you have this standard deviation in the p hat, which is the range of it's a measure of spread of these p hat values, or a measure of the accuracy, then remember from the empirical rule that 95% of samples lie within plus or minus 1.96 standard deviations of the mean, which means that your margin of error for 95% confidence is 1.96 times the standard deviation. And so your 95% confidence interval for P is P hat minus 1.96 sigma up to P hat plus 1.96 sigma. That's for 95%. Now, if you plug in P equals 0.5 here, and if you replace 1.96 by 2, you get back to 1 over root n here. So the 1 over root n is a special case, but it's an approximation. This is the accurate formula. And that for the sigma, and then using the sigma in the confidence interval. And that's for 95%. Using the empirical rule, you could work with other confidence intervals. For example, 68% is 1 sigma on either side of the mean, and 99.7% confidence that is within 3 sigma on either side of the mean. You don't really need to remember these because, well, they're rarely used. Most people use a 95% confidence interval. Now, let's move on to inferences about means. And I'll just introduce this quickly, and we'll get some examples of it later on. So when you're talking about inferences about means, you're actually looking at means of means, which is a little bit confusing to think about. But what you consider is that if you're looking for a mean value of some quantity, say, for example, the mean weight of something, or the mean cost of something, you can calculate it over a whole data set. But generally speaking, you'll want to make an estimate from a sample from that data set. So I've given an example here that you might have a cargo of apples, which might contain several million apples. And for some reason, you want to know what the average weight of an apple is in this cargo. Now, if you could do it just by measuring the weight of every apple and counting all the apples and getting an average. In this case, it might be 84 grams. That would be a very time-consuming way of doing it. So more typically, you take a sample of, say, 100 apples and weigh them and find the average weight was something, let's say 82.7, which should give you a fair estimate of what the real average is, but because there's going to be some randomness in your selection of the sample, it's not exactly the same. If you took another sample of 100 apples, you might get a slightly different average. Here I said 85.6. Again, it's not quite exact for the whole population. It's in the ballpark. And you can take another sample again, and you get another value, which is again close to the real population average. So what you're doing then is each of these samples has its own mean. So this is one of those which we could call X1 bar. This other sample has its own mean x2 bar, and this third sample has a mean x3 bar. If you take as many samples as you want, each one will have a sample mean x bar, and these x bars, it turns out they will on average be 84 if you do enough of these samples, but they'll be spread around a little bit. And we use something called the central limit theorem to determine, well, first of all, to say that this average, the average of these averages of the samples actually does match your mean of the whole population, but it also quantifies how much spread, what the standard deviation of all of these samples is, of all these sample means is. And that allows us to determine how accurate our sample mean is in terms of estimating the true population mean. That's it's a reasonably complicated concept, so it's worth dwelling on that and thinking about that for a while. It does take a while to realize that we're talking about the mean of these means here, which we label here mu of the x bars, which is the mean of the x bars, and the x bars themselves are the means of the samples. So we're interested on knowing that this mean of the means is close to the true population mean, and we're also interested in knowing what the spread of these means is. So let's look at the central limit theorem, how it's stated. And it says that for some certain conditions, which, and by the way, these conditions will always be met in the questions that you're asked, because it would require a more complicated statistical analysis if this isn't true. So in practice, you'll be asked questions for cases where this condition is satisfied, and there are two options. Either your original population has a normal distribution, which is very common, or if your sample size is big enough. Then these x bars, which are the means that you measure from each sample, that they will be normally distributed. The fact that they're normally distributed means that we can use all of the tools we've talked about before, as long as we know their mean, which is the mean of these means, which is this mu x bar, and we know standard deviation. And the central limit theorem tells us what those two values are, and it tells you the mean of the means will be the population mean, so that's easy. It tells us that the standard deviation of these sample means is smaller than the standard deviation of the actual individual data samples, and is smaller by a factor of the square root of n. So the bigger the sample you take, the smaller the standard deviation of the mean sample is, which means in practice that your estimate of the mean from the sample becomes more accurate as this value n gets bigger. Right, so what you need to do, you need to remember this, the statement of central limit theorem, what it means, and these values. Well, the simple thing is that the mean of the means is just your original mean, but more importantly, that the standard deviation of the sample means is your original standard deviation divided by the square root of n. So that needs to be remembered. And once you have these, you've got a mean and a standard deviation for these sample means. Then you can start to use the empirical rule and the standard normal table. If you're dealing with a 95% confidence interval, you can use the empirical rule, which is this one, 1.96 sigma on either side of the mean. If you're more generally, if you're not using 95% confidence interval, we need to go to this z-score, where you go to z for the standard normal, transforming from x to z. In this case, you're not dealing with x, you're dealing with the x bars. And the sigma that you use is the sigma x bar that you've worked out from here. Otherwise, though, it's the same procedure as for using the ordinary normal distribution. But again, in the particular case of the 95% confidence interval, you don't need to use the z-score. You can go straight to the empirical rule and say that in the case where you measure x bar, you measure a sample, you measure the mean of the sample, and you want to know what the mean of the population is, you can say that the mean of the population is going to lie within 1.96 sigma of your sample mean. But it's this sigma here then, this reduced sigma, which is the standard deviation of the means. So that's the process. This actually needs, we need to go through examples of this, and the best way of doing that is going through exam questions where they ask this quite frequently. So to illustrate all of this, we'll go through quite a few exam questions in a few minutes. This might be a good time to take a break.
Hello, everybody, and welcome back. So, okay, Frank, I'll let you take over this share again from here.
Okay, let's start again. Before we continue, I just, there was a typo earlier on in a previous slide where I had, let me find a pointer, where I had mistakenly written 0.5 there. In fact, the tabulated value corresponding to Z1 is 0.5, but it's actually a Z1 of greater than 0 is what is tabulated. So just in case there was any confusion there. Okay, so let's carry on. I also had a typo somewhere here as well. I think I had a -2 there, so I fixed that too. Okay, so we were here. We were talking about inferences about means. And the important thing to know there is central limit theorem, that when you're taking a sample and measuring the mean value in a sample, central limit theorem says you can use the same mean as the population mean, but the standard deviation is reduced by square root of n relative to the data in the original population. Another point is sometimes you won't have sigma from the original population, but you will have sigma from your sample. So you can use that sigma in this formula if that's all that's available. And then using this mu and this sigma, you proceed as before for the empirical rule. In this case, this is the empirical rule using mu and sigma. Or you can work at a z-score using this value of sigma and that value of mu. Okay, so let's carry on. Hypothesis testing. This is, using the confidence intervals to test a hypothesis. And a hypothesis will be an assumption that something is true. And generally, there'll be a null hypothesis, which is a default assumption that nothing has changed from what was before, or that some stated expectation is true. And usually a confidence level of 95% is what's used to test the null hypothesis. And that means that whatever you're looking at, whether it's a sample mean or a proportion, it should lie within 1.96 standard deviations of the expected mean or proportion, or vice versa. Sometimes you want to test that the expected mean or proportion lies within that many standard deviations of the sample mean or proportion. They can work either way. An equivalent to that is to say that the z-score should be between minus 1.96 and 1.96, because the z-score is the number of standard deviations that you are from the mean. If you do meet this condition, it means you can accept the null hypothesis. If not, you reject it. Now, you can choose to state it the other way around, to state the null hypothesis to be the opposite assumption. But generally, you don't. Generally, you take the null hypothesis to be the one that's the default, or the one that implies no change. We're going to run through some examples of that in the exam questions. A related topic is a test of significance. So we're talking about p-values here. Now, a significance test is often run to 5% or 0.05, and that's exactly equivalent to a 95% confidence interval. Now, p-value, though, it can go a bit further than that. P-value is the probability that a given result, or something more extreme than that result, could have occurred purely by chance, even with no change to the underlying data. So if you're testing to p equals 0.05, which is a confidence interval of 95%, you can use the empirical rule. But the more general technique is to work out the z-score of whatever result you have, and then use the standard normal table to work out the probability of the z-score, or something more extreme than that z-score, happening. And again, we'll go through some examples in the exam questions. And by way of interest, it's common if you want to publish a scientific result, you need to show that it is a statistically significant result, and the threshold that's generally used for publication is that the p-value must be less than 0.05, which means that the result you're showing isn't likely to be just some random result, but that there is something real happening underneath. Right, so now there are a lot of concepts there, and they really need to be illustrated with examples, and the best examples are the exam questions. So I'm going to try to run through 3 or 4 exam questions on statistics from the last 5 or 6 years. Obviously, there was none this year. Now, it can be a bit daunting reading an exam question to decide exactly how do you go about it, but there are generally some hints in the question. If you do see 95% confidence interval mentioned, or equivalently 5% significance test, then that probably means you're going to use the empirical rule, which means you go 1.96 standard deviations around the average for your confidence interval. So for inferences about means, that would be this formula, or the equivalent formula for inferences about proportions. Sometimes, though, you can use the slightly less accurate formula for the proportions, using just 1/√n. Now, if you don't see this, then the chances are you'll have to work with the z-scores and go and use the tables. And in a lot of questions, they might have one part A where you do use the empirical rule, and maybe in another part you have to use the z-scores. We'll be showing a few examples of that. Okay, so let's dig into some examples. In 2015, there was question 2 on paper 2. And here's an example for just using a standard normal with 95% confidence interval. So in this case, they're talking about a survey of 100 shoppers. Survey means they've taken a sample of 100 and it's selected from a larger number of shoppers. And they find that sample mean was 90.45. Now we don't know what the total mean for the whole population was, but for the sample, the mean was 90.45. And the standard deviation of this sample, which you can use to estimate the or as an approximation for the standard deviation of the full population, is 20.73. So you want to find a confidence interval 95% for the mean amount spent in the supermarket on that day. Right, and because you're dealing with a sample mean here, you use the central limit theorem, which means you need to first of all work out the standard deviation of the means, which is sigma over root n. As I said before, if you don't have the sigma for the whole population, you can use the sigma for the sample here, which we're given as 20.73. And applying this formula, we find that the standard deviation of the means is 2.073. Whereas the central limit tells us that we can use the mean, the original mean, as being the same as the mean of the x-bars. So your 95% confidence interval, then it tells you that the population mean lies within 1.96 sigma, 1.96 standard deviations above and below your sample mean. So plugging in the numbers, you have your sigma is 2.073, 1.96 times that, and you add and subtract that from 90.45, and that gives you a range of 86.39 to 94.51 from you. Okay, and we're 95% sure that the average spend of the population was actually in this range. And you just state it in this form, and that's your confidence interval, that's your answer. That's part A answered. Okay, so that's just a direct application of the central limit theorem, so it's relatively easy. Part B of that same question, that the supermarket has claimed that the mean amount was 94 euros. So it says, test the supermarket's claim using a 5% level of significance. Well, 5% level of significance is the same as a 95% confidence level for your interval. And the 95% confidence level, or sorry, the 95% confidence interval, remember, was this 86.39 to 94.51 range. And clearly 94 lies inside that range. But formally, they ask you to state your null hypothesis and your alternative hypothesis and your conclusion. The null hypothesis is that the average spend is 94 as claimed. And the alternative is that it's not, it's the opposite. And this, so we're using 95% confidence interval. This was our confidence interval, 86.39 to 94.51. Clearly, 94 euros lies within that confidence interval, and that confirms the null hypothesis, or at least it's consistent with the null hypothesis, subject to 94 to a 95% confidence. And that means we accept null hypothesis. We don't have a good reason to reject it. And that means the supermarket's claim is plausible based on our measured sample. Right, so a lot of words just to say that, yeah, 94 is within that 95% confidence interval. So we accept this claim from the supermarket. Okay, and that's the general process. You state a null hypothesis, which is your default position, and see, is it consistent with your 95% range, and then either accept or reject the hypothesis on that basis. Okay, now part C of that same question is they ask you to find the p-value of the test you performed in B. Right, so the p-value is, instead of looking to see whether the 94 lies within the range, we actually look for the p-value of that 94. Or actually, it's the p-value of the relationship between the 90.45 and the 94. Right, so for the p-value, we need to work out the z-score. Now, generally, the z-score is x minus mu over sigma. In the case of a sample mean, the x is actually the x bar, which is the sample mean, and the sigma becomes the sigma x bar, which is the standard deviation of those means. So the x bar here was the measured mean, which we have, which is 90.45. 94 is the population mean that we're assuming, and the standard deviation of the sample means is 2.073. We've worked that out before, and we find that the z value is minus 1.71. What this means is that that the measured value of 90.45 is that many standard deviations below the claimed value of 94. And we want to know how likely is it that, obviously there's a difference there, how likely is it that such a big difference could have occurred by chance? So if we look at the standard normal curve here and look at the z value of minus 1.71, then this hatched area here is the probability that you could get a value that was more than 1.71 standard deviations below your mean, or at least 1.7 below the mean. But of course, it could have gone the other way as well. A similar error would have been if you were 1.71 deviations above the mean or more, which is this hatched area up here. So the total of those two cross-hatched areas represents the likelihood that you could be at least 1.71 standard deviations away from the mean, which is what you've measured. So how likely is that to happen by chance? You work out these areas, the total of those two areas. So we're looking at the p of z is less than or equal to minus 1.71 plus the p that z is greater or equal than 1.71. Neither of those is directly tabulated, but remember that this P of Z being greater than 1.71 is equal to 1 minus the P that is less than, right? Because we're looking at the total area under the curve as 1 and subtracting everything below here to get what's above here. Looking at the table then, for 1.71, we find 1.71 is 9.9564, this value here. So 1.9654 is the area under here. Subtract that from 1 and we get the area under here, which is 0.0436. So that's 0.0436 under here. We use symmetry to say that this over here, this area is also 0.0436. And the p-value is a sum of those probabilities, which is 0.0872. So overall, there's an 8.7% probability that we could have got an answer this far away from 94 or more. And that's a reasonably high probability. It's more than 5%. So we say, yeah, that could have happened. So we don't reject the null hypothesis. So that's the explaining what this value represents. Okay, the p-value is 0.0872, and what it represents is a probability that this could have happened, and that probability is more than 5%. So we don't reject the null hypothesis. Right. Okay, that was the 2015 question. If we don't have any questions on that, I'll look at the 2014 one. Now, the 2015 was a question about inference of sample means, or inference of population means. 2014 is about inferences of proportions. So that's the other class of problems of inferential statistics. Right, and we're told that there's a generic drug that has a success rate of 51%. That 51% is a proportion, so it's a p equals 0.51. And they're saying that there are two new drugs, A and B, and they have two groups of 500 patients. So for the first group of 500 patients, they're saying it was successful for 296. Right, so the proportion for the generic drug, remember, was 0.51. We work out the proportion for drug A, and that is p hat, and that we're told is 296 successes out of 500, so it's 0.592. Now, they ask us to use a hypothesis test at 5% level of significance to say whether there's sufficient evidence to justify the claim that it is successful. So 5% level of significance, that's the same as 95% confidence interval. And p is close to 0.5. You know, the p is 0.51 in this case. So you're justified in using the approximate formula, the simple formula for the margin of error, which is just E equals 1 over root n. And that's 1 over root 500. So when you work it out, it's 0.0447. So your confidence interval is P minus 1 over root n, or P minus E up to P plus E. And working out those numbers, we find that your P hat should lie between 0.4653 and 0.5547. Now, how do we use this? Well, we state a null hypothesis. The null hypothesis being that drug A is the same as the generic drug. which is the status quo. For some reason, it auto-corrected this and capitalized this into the name of the band, but that's not what's meant here. It's just the status quo as being the nothing has changed status. However, we find though that the measured p hat 0.592 doesn't lie within this confidence interval. It lies outside the range, so we reject the null hypothesis, and that means that the drug A is probably better than the generic drug, supporting the company's claim. Right. So now the second part of that question, they say the null hypothesis was accepted for drug B. If we apply the same null hypothesis as we had before, which would, in this case now would be that drug B is not any better, which means that its p hat must lie inside this confidence interval if we were to accept the null hypothesis for drug B. So let's look at that. To accept the null hypothesis, P must lie inside this confidence interval. So it must lie within those values. And they're looking for the greatest number of patients that's compatible with that, which would be the upper value here, that P must be no bigger than this, P hat must be no bigger than this upper value. So our maximum value of P hat is 0.547. But P hat, of course, is the number of patients that were successfully treated divided by 500, less than 0.5547. Multiply across, you find that X must be less than 277.3. But of course, X must be an integer because it's a number of people. So the maximum value it can be is 277. Okay. Moving on. Looking at 2016 paper. Now, this is one of the long questions here. Question 9. So let's take it one step at a time. First part, they're talking about, they have some earnings data, and they're saying that that they have statistics for all the population. They have the mean value, 39,400, and a standard deviation of 12,920. Now here, this isn't there's no mention of a sample here. So we're just working with this normal distribution here of the full population. You don't need to worry about inferences of samples in this case. It's just a direct look at the normal distribution of this data. So part A, they want to look at what percentage of full-time workers earn this much or more. Okay, now in this case, there's no mention of 95% confidence interval or anything like that. So we're going to need to use the Z-score here and use the tabulated values to work out this. So we start with the mu is this value, the sigma is this. We can't use the empirical rule. We want to calculate the Z-score that corresponds to 60,000 in order to see what fraction of people are above that. So work out the Z-score, it's X minus mu over sigma, 60,000 minus 39,000 over 12,000. We get a Z-score of 1.5944. Another way of stating that is that 60,000 is 1.59 standard deviations above the average. We want to calculate the probability that Z is greater than or equal to this. And And as usual, we need to use, because the tabulated values are for p is z less than or equal to something. So we need to go 1 minus p of z less than this. And that, let's flip to the tables again. It's 1.5944. The closest value we'll get is 1.59, which is over here, and that's 0.9441. So it's 1 minus 0.9441. And this is telling us that 94.4% are below this 60,000, but 0.056, which is 5.6%, are above 60,000, which is what you're asked to show. Again, make sure it's accurate to one decimal place here. Okay, so that was just a direct use of the standard normal table for a normal distribution. Now, part 2, they ask you for a subsidy for, they want to give a subsidy for the lowest 10%. So you need to know what level that occurs at. So what is the salary number, which is greater than the lowest 10%. So we're going to need to work in z-scores again to work this out, and work from the z-score back to a salary. Right, so we want a z-score which is greater than 10% or greater than 0.1. So we're looking at value of z here, which is bigger than 10%. And of course, that isn't shown on the table. So we actually need to use symmetry here to look at a corresponding value where I'm calling z prime, which is where you would have a 10% above this z prime, and that means that 90% would be below this z prime, and that's something that is tabulated. So we're looking for a value of z prime such that that z is less than or equal to z prime is 0.9, and we find that on the table. We just look for 0.9 in the table, and the closest value there is 1.28. Right, so we see that z prime here is plus 1.28. Now, let me just go back to the normal table here and see what we're doing here. Instead of looking for a z number and reading off the area under the curve, we know that the area under the curve must be 0.9, and we want to find that value in the table, and it's the closest number to 0.9 is this one, and read off what z value that was. Well, there's a 0.08 here added to the 1.2, so it's 1.28. Okay. Right, so this z prime is 1.28, but we're actually looking for z. We use symmetry to find z prime, so the symmetrical value down here is minus 1.28 for z. Now that we know what z is, we want to convert that back into an x value. All right. So the formula for z was this. We need to turn this around to find a formula for x in terms of z. And you find that x is mu plus z sigma. The mu, as before, was the average salary was 39,400. The standard deviation sigma was 12,920, and the Z in this case is minus 1.28. So work that out and we get 22,862. So an X of 22,800 corresponds to a Z of minus 1.28. In other words, it's 1.28 standard deviations below the average salary. Okay, and that's the level of income at which the threshold for paying the subsidy is. And I've rounded that off to the nearest euro as they asked. Right. Okay, part 3. Now they're asking slightly different question. Now they're talking about a sample. So now we look at the inference of sample means here. And they have a sample of 1,000, and they find that sample has a mean of 38,280, which is a little bit different from the mean that we had before for a whole population of 39,400. And they're asking at the 5% level of significance, so that's 95% confidence interval. So we can use the empirical rule here if we need to. And that we want to see whether this is consistent with the original stated average of 39,400, or whether that mean has changed from 39,400. Okay, so we need to state a null hypothesis and an alternative hypothesis. And the null hypothesis you would choose here is that, well, actually nothing has changed. The mean income still is 39,400, and that this new sample mean is consistent with that. The alternative hypothesis is that the mean income of the whole population has changed since the first survey was done, and that we need to change our population mean. Right, so let's look first of all at our samples data. Our sample data is, we've got a new sample mean of 38,280. We'd like to know what the standard deviation around that is. And that's given by the central limit theorem, sigma over root n. Root n here is root 1000. So the standard deviation of the means of the sample means is 408. And then we can see how far our sample mean is from our original population mean in terms of a Z-score. And sorry, again, I've got a typo here. It's just this number minus this number divided by 408. And we find that the Z-score is minus 2.74. Now that's more than 2 standard deviations below the mean, the original mean. Or put another way, the 95% confidence interval in terms of the Z-score is minus 1.96 to plus 1.96. We're outside that confidence interval, and so we reject the null hypothesis, and we assume that the mean income of the general population has changed. Right. Then part B of that question is now we're looking at a different data set, and they've surveyed 400 full-time farmers. That's telling you they're taking a sample. This is samples data again, with a sample size of 400. And that's selected from all the farmers and found a mean income of the sample with a standard deviation. So the mean income in the sample is 26,974, and they had this sample standard deviation of 5,120. and they're telling you that, that there's a normal distribution for the whole population. So they want you to work out a 95% confidence interval for the mean income of all of the farmers based on this sample of 400. Right, so for a 95% confidence interval, you can use the empirical rule, which states that you're going to be 1.96 standard deviations on either side of the mean. So the true population mean, which is what you're looking for in this case, is going to be your sample mean plus or minus the 1.96 standard deviations. So let's work out standard deviation first. It's sigma divided by root n for sample means. 5,120 divided by square root of 400, which is 256 in this case. And your sample mean is this number 26,974. So just apply this formula directly. So you're taking 1.96 times standard deviation from your sample mean to get this 26,472 for the lower limit, and you're adding 1.96 times sigma to the mean to get your upper limit of 27,475. And that's your answer then. This is the range of, you can be 95% sure that the actual population mean lies between these two values. Now, part C, they're telling you that, well, actually, it's not a normal distribution for the for farm sizes, and they're asking you, why would you take a large number of large random samples of farm size? And the reason you would do that is because the central limit theorem tells you that if you do that, the sample means will be normally distributed. And of course, the larger the samples themselves are, the smaller the standard deviation. So those are the reasons you would do those two things. So that statement is all you need to answer part C. Part D. Here, they're asking you for, well, they're telling you actually the margin of error and asking you to find the size of the sample. You don't have much information here because all you have is the margin of error. You're forced to use this simplified formula for the margin of error. E equals 1 over root n. You're told that that is equal to 0.045. So root n is 1 over that. So n is 1 over that squared. And n is, well, you take the nearest integer because it's a number of people. So it turns out to be 494. Okay, and that's the end of that. That was one of those long questions, but the individual parts to it were all relatively straightforward. And finally, there was last year's question. It's another long question. Paper due question 8. And similarly, there are lots of small sections in this. None of them is individually difficult. So let's just work through them. Part A, and they say, okay, details on 800 cars. So we're dealing here with a sample of 800 cars. So straight away, it's inferential statistics that we're dealing with. And they look at the sample and they say a certain number of them are new. So you're looking at this characteristic, that how many are new versus not new. So that's a proportion we're dealing with. And they ask you for 95% confidence interval, so you can use the empirical rule of the proportion of new cars in that road. So they're looking for the total population proportion based on the sample proportion. Okay, so let's first of all work out what the sample proportion is. It's 174 over 800, so p hat is 0.2175. Now, this number is a long way away from 0.5, so you can't use the simple E equals 1 over root n for the margin of error. We need to use the accurate formula instead of E equals 1 over root n. So the accurate formula is got by looking at the standard deviation of the sample proportion, which is the square root of p times 1 minus p over n. Plugging, we don't actually have p here, we have p hat, so we use the p hat instead. So use the p hat value for p, and it's 0.2175 times 1 minus that over 800. Square root of all that is 0.014586. We're keeping a good number of significant figures here for the time being, because we want 4 significant figures in the end. And now, because it's a 95% confidence interval, we can use the empirical rule, which is 1.96 standard deviations on either side of p hat to find p. P is what we're looking for. So 1.96 times this sigma p hat, we subtract it from our p hat and get this 0.1889 for significant figures. We can also, on the other side, we add 1.96 standard deviations to p hat and get 0.2461. And then this is our range, our confidence interval, 95% confidence. Okay, so that's just a direct application of the formula for the confidence interval for the sample proportion. Okay, part 2. Now we're looking at, again, the same sample of vehicles, but we're not looking at a proportion anymore. We're looking at their mean speeds. So we're looking at inferences about means from the sample in this case. And they do give the sample mean 87.3 and standard deviation 12. And they're asking you what proportion is over 95. Now, in this case, there's no mention of 95%. You can't use the empirical rule. You're going to need to use a z-score in this case. So we work out the z-score corresponding to the value of 95. As usual, the z is x minus mu over sigma. And we have the x, which is 95. We have the average mu, which is 87.3 over 12. And that is a z-score of 0.6417. The tables, look at the table for 0.64 over here to the 0.04 is 0.7389. Right, so and this is that p is z is less than this, so this is the proportion that are going lower than 95. They ask you for the proportion going higher, so it's 1 minus that 0.73 is 0.2611. So that's 26.1% of cars are going faster than the 95 from this sample. Now, you might wonder why we use the sigma, just a straight sigma rather than the sigma divided by square root of n. And that's because for this part of the question, we're just looking at our 800 vehicles. we're not comparing them with the larger population. So for this part of the question, the sample is the whole population, and we use the full sigma. Similarly, part 3, we're told 70% are higher than this speed, and you want to find what speed that must have been at. So again, we need a z-score, but now we don't know what a z-score is, but we do know that a z-score must correspond to a tabulated value of 0.7, because the probability that z is greater than this value is 0.7. So actually the tabulated value would be 0.3, because 0.3 are less than this, and the tabulation is always of the number that are less than your z. Okay, so 70% are higher. That means 30% are lower. So we're looking for a value of z which corresponds to 0.3 in the table. So let's look at the table and try to find 0.3. Well, unfortunately, the table starts at 0.5, so that's no good. So we need to change and exploit symmetry, and need to look for, instead of the p of z less than or equal to z, we look for a corresponding symmetrical value, which would be the pz greater than or equal to z prime being 0.3, which means that the pz less than or equal to z prime we're back to 0.7. So there's a bit of flipping and flopping there between 0.7, 0.3, and 0.7. So you might need to actually, if you need to draw it out on the normal curve to see what's happening there, to confirm that we do get the point back to 0.7 here. And we need to find out what z prime is gives you a 0.7. And the 0.7, in this case, the closest value is 0.52 here for z prime, right? And then exploit the symmetry and go back to z. So z is minus 0.52. So just to clarify what I've done there, for a z of 0.52, that tells you that 70% are less than 0.52, which means 30% are greater than 0.52, which means that 30% are less than minus 0.52, which means that 70% are more than 0.52. So I know that's a bit complicated, but these are the kind of mental gymnastics you need to go through when you're using the z-scores when you've only got half the table available to you. Okay, when you finally end up with a z-score of minus 0.52, you need to convert that back into an x value. Again, using the same mu of 87.3 and z of 12, oh sorry, sigma of 12, and you find 81 kilometers an hour. And that tells you that 70% of speeds were higher than 81 kilometers per hour. So this is the speed he was traveling at in order for 70% to be faster than him. Clearly this is below the mean, and that if you had gone wrong somewhere with all this jiggery-pokery of using the symmetry and changing from greater than z to less than z, you might have come up with an answer that was greater than the mean, and that would immediately you'd know that was wrong, because 70%, it must be a number that's lower than the mean in order for 70% to be higher. Okay, part B. Then, okay, this is just a verbal question. They're telling you, okay, they've got a sample of 100 cars. And now they want to see whether the average speed based on this sample of 100 is different from your previous average speed, which is based on a bigger sample. And they said, okay, they ran a hypothesis test at 5%, and they found a p-value. They've written a pp here, but they just mean a p-value of 0.024. And based on that, what can they conclude? Well, a p-value of 0.024 is a lower probability than 5%. And since it's less likely than your threshold, you say, well, that's unlikely to be consistent. So you would reject your null hypothesis. And that means you should conclude that the average speed had changed. Following up on that, though, they ask you to find out what average speed would have given you this p-value of 0.0224 or 0.024. And actually, there are two values that could have done it, but they help you by telling you that it's lower. So it's a lower value that you should choose. Right, so this p-value of 0.024, for a p-value is the probability that you had a value that extreme or more extreme. So on the Z curve, to get a p-value of 0.024, you would need to have two sets of extreme values, one extreme in one direction, one extreme in the other direction, each of which has a probability of 0.012, because 0.012 and 0.012 would add up to 0.024. And you need to find the Z value beyond which you have 0.012 probability of it happening. And the corresponding minus Z value were beyond that. In the other direction, you would have a 0.012 probability of it happening. Right, and so you're looking for a Z score where you would have a PZ greater than this Z of 0.012, which means there's a P that the Z was less than it of 0.988, because that's what's tabulated. There's a 0.988 for all of this down here below this, and that's what's tabulated. So you go into the table, look for 0.988. It's going to be on the next page. 988. This is the closest value here, and that's 2.26. So Z equals 2.26 is this point over here, and its negative counterpart, again, use symmetry, it's going to be at minus 2.26. Right? Now, to convert that back into a speed, you need to use the formula for converting between X and Z. In this case, though, because you're dealing with a sample, you need to use the standard deviation of the sample mean. So let's work that out first. It's sigma over root n. The sigma was 12 divided by square root of 100, which is the sample size. You get 1.2. And you can then use this formula with this sigma of the means in the formula. Rearranging this to find a formula for x, you get x equals mu plus z sigma, where this sigma is actually the sigma of x bar. And x is then 87.3 minus this z score is minus 2.26 by 1.2. Note that we're using the negative z prime in this case rather than positive z, because they told you that it was the lower limit was the one that was hit. And when you work that out, you get 84.6, correct to 1 decimal place. Okay, so that's an example using p-values. So that was the last of the exam questions that I had to go through. And so we're coming close to the end of the time. So there's a few minutes in case there are any outstanding questions, or if there's anything people would like me to double back on and go over again. So I'll hand back to Eamon there.
Thank you, Frank. That was, yes, hello, Frank. Thank you, Frank. That was an excellent presentation. At the moment, I don't see any questions coming in from the students.
Okay.
Just as I'm just finishing up there now, I'm going to, and we can see if any questions come in the meantime. We've got one coming in here now. Oh, we've got one question coming in. Do you use statistics in your work? Do you want to answer that live?
I do myself. Generally, we do. I mean, personally, I work with cable systems for cable TV systems and for internet delivery. So one of the things we work with is the distribution of cable lengths, because some services only work over particular lengths of cable. So we have statistics for the distribution of cable lengths, and we use them to determine what percentage of customers can be reached with a particular service based on the distribution curve of the cable lengths. And we might find that 85% can be reached with this new service, with this new technology. And then we tell our customer, who are cable operators, that you're going to need to run new cable out to 15% of your customers if you want to use our product here.
Thank you, Frank. That was a nice answer to actually a very good question. So I don't see any more questions coming in. So I just want to tell you about next week's tutorials. So we've had 12 different topics covered by the tutors over the last 12 weeks. And next week, we're going to have 2 sessions, one for paper 1 in the morning and one for paper 2 in the afternoon. So in the meantime, there's a lot of statistics information in the log tables, formula and tables booklet, and also make sure Frank did a good few questions there. There are more questions, as you hopefully know by now, in the official examinations site, examinations.ie, and they've got marking schemes and everything there also. And maybe also the Khan Academy is another place where you can find resources. So until then, I'm going to say thank you to Frank for a great presentation, and hope to see you next week for the exam questions tutorials. We've got two, as I mentioned there, one is starting at 10 and the other starting at 2 p.m. The times here are approximate. I'm not sure exactly how long the tutors are going to take for each one, but we've timetabled in 2.5 hours. So hope to see you then, and in the meantime, bye for now.